to reach there. And then when they start, you see that they keep progressing until they reach a certain synchronization point. So see now they're both at 63. They're waiting for some other node. Now they're going to start again. They're going to go to 64, 65, etc., etc. So the negotiation obviously initially, it takes a while to get things running. You see that now the daemons are starting in each node to actually process the MPI events. And while this thing is running, we can actually look at some of the statistics we can pull out of the database. Now, obviously, Postgres has to wake up, so it might take a little longer. But once you wake up, it'll be fast. Just 1 second. So the reason why we decided to also have a database backend is to be able to store multiple experiments and being able to retrieve data without having to browse through multiple files. So now what we're showing here is, in this example, for example, is the instruction count, which is sort of, the IPC basically of these execution accumulated. So for each node, each line represents in the IPC of a single node. So they were doing almost nothing through 600 milliseconds, and this is refreshing dynamically. Now you see that something's starting to happen. And of course, because I noticed that, as I notice now, I think that something is not actually starting out. Okay.
Laptop is not the best.
Right. No, actually, I think it's starting. What happens is that it takes a little longer, and it's a little undeterministic in some cases, because some machines, may not respond. And like in reality, when you're running an MPI benchmark, well, you see, you can get the statistics of each node, and then I can see. Let's see what we get here. You can get statistics of the network. So this is, for example, the number of bytes read from the network interface, throughput per second, whatever it is. And you can get, as you get before, all the statistics about if you're individual nodes. Here we're looking at the Dcache read miss behavior of each node. They're all added up. So here they're missing a lot because they're starting. Here they're getting into some initial behavior, or the level 2 cache. In this case, I believe it's a shared L2 for all nodes. And so again, you can zoom in into whatever behavior you want to observe. And okay, well actually now it's starting. So now we're starting CG, which is the first of the 6 NAS benchmark that we're going. Before we were actually waiting for all nodes to come up and do the NPI negotiation. But you imagine that. So this is like setting up things in a real cluster. So these 2 nodes, I can, assuming this can go as fast as I want, I can actually get another console prompt and log in here while the simulation is running. It takes a little longer because now we're sampling, etc., etc. But you see, it's almost interactive. Right? I'm actually, while we're doing this, the whole thing that Daniel explained before is going on in the background. So this is being sampled. I'm doing execution, and here what I can do is again, SSH to N01. I'm going to SSH to another simulated node, which is the one running the benchmark. So it might take a while, but you'll see that basically it's the real world here. So you can imagine that we're doing all of this stuff. And while I'm doing this, I can get statistics. So now, again, things are starting to run a little more, and so you get more accuracy, etc. So this is basically our cluster simulation environment that is very close to, there we go. Okay, so now I'm on the other node. Start from this node, so I can do whatever. And of course, if I do something here and interact, I'm going to see all the metrics changing. And you can get everything going underneath. This one, the caches. You can see now the NIC starting to be a little more active and actually sending stuff. Because now it's running the CG is still running the CG going through the execution. Now we scale these up to in the order of 100 nodes running on the order of 40 physical hosts in parallel. And in this case, we're synchronizing with an adaptive quantum every between 5 and 100 microseconds, depending on the traffic. So if there's traffic, we're cutting down the synchronization interval. When there's no traffic, or there's an area of simulation where we don't see any packet moving on, then we speed up the execution by loosening the synchronization. That pretty much sums it up, and I think I can kill this. We have time for the disk simulation?
Yeah, we have
I think so.
5 minutes, so
Okay, we kill this.
We should also be talking about the licensing.
Yeah, so let's show the disk just as an example. I think the disk is interesting because it shows an example of integration of an existing tool within COTSon itself. And then we can close up with how to get it if you're interested.
okay, so
Should I just run it?
yeah, I would like to cover a little bit, so then explain this part. So basically, so the main explain that we receive 3 kinds of events. So all the CPU and memory events on the one side. We also receive all the network events, Paolo showed now. And the last kind of events we receive are those related to this activity. So initially we had a simple model for this, which we set up to configure it with a particular capacity and size block. And we at the end receive how much time a particular read or write to a disk takes. So what we have done recently is integrating disk sim. This sim is this simulator, whatever known in this for the people that work in disk research, and we basically have integrated using one interface they provide. So the good thing of this sim is that they provide some models of real disks that are validated, so we can use them in our simulations. So one of them is this. When I show an example of this disk, it's Seagate Cheetah 4LP. It's a very old disk, 4 gigabit, 4.5 gigabit disk. So we're going to show how the simulation works when we have this kind of this. Yes. Right. In this case, we have a benchmark called COTSon that measures this bandwidth of the machine. We are not using CPU timing, so basically all the timing we receive here is due to this activity and not to the CPU. Okay, this is a benchmark running. It performs some kind of test, random reads, writes, and so on.
Right, so you can actually look at the disk traffic if you're interested.
Yes.
So let's see. So now we're looking at this is the total delay from read and writes of this execution. So for example, the benchmark first does all the, I believe they're starting with all the writes and with all the reads. Oh, I guess this is not the live one, this is the one we saved. So let me go back. Change this to the one that's being actually executed. So as you see, as we are running this, we're actually starting to see some activity. This is sampled fairly, coarsely, just to give an idea of, the kind of statistics you can get out of this. And it will take a while to jump through this benchmark. But at the end, what we could see is that, the statistics of this thing match what the COTSon benchmark tells us. So, we're running with, 4 megabyte per second disk, or 5, 6 megabyte per second, and all this. And actually, the statistics there tell us exactly what this sim tells us, which means that, we're providing the right time feedback for the application to believe that this execution is indeed of 5 megabyte per second, as, and then when you can get into the statistics of this sim itself, you can get more details than you ever want to know about the disk spinning, what about to finish it.
That's it.
So see now, we're running an extremely coarse-grained sampling with functional, large functional simulation because we don't care about instructions. Here we just care about this feedback going back, the timing being sent correctly to the functional simulator. So do you have any last questions before we talk a little bit more about mechanics?